Hello everyone, welcome to the Gaia Open Research Lecture Series. So today I will give an introduction to the mathematical theory on the optimization. And so let's look at the first slide. I will give an example of the optimization problem in finance as motivation. So let's consider a portfolio which is described by a vector x. So x is a vector with component x1, x2, and up to xn, where x1 denotes the number of the first financial asset in the portfolio. Okay, and xk is the number of the kth financial asset in the portfolio. Okay, the value of the financial asset is denoted by S, and we consider a one period situation and with time 0 and time 1, and so that we can compute the value of the portfolio value at time 0 and the portfolio value at time 1. So the portfolio value at time 0 is given by the inner product of the vector x and the vector s0, and the portfolio value at time 1 is given as the product of the vector x and the vector s1. Okay, with this one we can introduce two basic portfolio choice problems. Okay, the first one is to maximize the utility function. Okay, we can choose the composition of my portfolio, which is described by the vector x. Okay, and of course we try to choose the best x to maximize my utility. And we can also consider a minimization problem to minimize the risk or the cost function. Okay, now let's move to the second slide. In real situation, we can have different constraints on my strategy x. Okay, for example, we may have the budget constraint. Okay, this means that the initial value of my portfolio pi 0 should be less or equal a constant c. So this constant c is my initial wealth, total wealth, because the utility function is usually an increasing function. So in order to maximize my utility function, I can increase my portfolio value, my initial investment, and of course we should add this kind of budget constraint in the portfolio optimization problem to make it realistic. In this case, we will obtain a maximization problem under constraint. For example, I maximize the utility function subject to the budget constraint pi 0, the initial wealth of my portfolio is less or equal to the constant c. Or the minimization problem of the risk, or minimization of the risk subject to the budget constraint pi 0 is less or equal to constant c. So we have this optimization problem under constraint. Now we move to the next slide, slide 3. We will give some abstract formulation, mathematical formulation of the optimization problem. Okay, and we give the first formulation is just we have a function f is defined on Rn, okay, and we have a subset of Rn, and we minimize this function f on the set B, on the subset B of Rn. A second formulation of optimization problem is to minimize this function, but subject to the constraint. And there are two kinds of constraints. Mathematically, we can consider the inequality constraint. For example, g of x less or equal 0. or the equality constraint h of x equals 0. Okay, so we have the second formulation is minimize function f subject to the two constraints. One is inequality and the second one is equality constraint. Okay, now let's move to the next slide, slide 4. We look at the first optimization problem. Abstract optimization problem is to minimize a function f of x. Okay, and for this minimization problem, a very classical method is the Euler's first order condition, which is given as follows. So if x is a minimizer, if x star is a minimizer, then the derivative of function f should be 0. In the multi-dimensional setting, we will replace this derivative by the gradient. The gradient of f of x star is 0. Okay, so we can look at the picture on the next slide, the slide 5. Okay, we have a function with the blue line. Okay, and then on the picture we can see that on the minimum point of this function, the derivative will be 0. Okay, and to give an idea of the proof, okay, we just take an arbitrary point x. So if the gradient of x is not 0, then we can find that we will be able to improve or find another point such that the function value, the f of this point is smaller. Okay, so the initial point x will not be a minimizer. So mathematically, if the gradient of, if we look at the end of slide 4, we see that if the gradient of fx is not 0, then we can find a vector v such that the product between v and the gradient of f is strictly negative. And in this case, we look at the value of f of x plus epsilon v. When epsilon is small enough, we observe that with Taylor expansion, this value is approximately f of x plus epsilon v times the gradient of f of x. And in this case, we see that v times the gradient of f of x is strictly negative. So this value, this sum is strictly less than f of x. And so that x cannot be a minimizer because the value of f of x plus epsilon v is strictly less than f of x. So f cannot be a minimizer. And in fact, in this proof, we can find a gradient descent algorithm to find the minimizer. Okay, now let's move on the next slide, on the slide 5. We can see that if we can provide iterative algorithm to find the minimizer of the function f. So given a point xk, we can find another point xk plus the gradient minus gamma k times the gradient of f xk. And in this case, on the point xk plus 1, the value function, the value f of k plus 1 will be less than f of xk. Okay, of course, implicitly, if f is a convex function, and we can mathematically prove that this algorithm will converge to the minimizer of the function. Okay, next we will look at the second formulation, abstract formulation, or on the optimization problem. Okay, the second formulation is optimization problem under constraint. We minimize the function f of x subject to the first constraint, inequality constraint g of x less or equal 0. The second equality constraint h of x is equal to 0. For this problem, the most classical method is the Lagrange method. Okay, and to present the Lagrange method, we can consider two steps. The first step, we reformulate this problem, equivalent formulation. We provide the equivalent formulation. Okay, we penalize the constraint with a constant lambda, a positive constant lambda, and any constant beta. And we maximize over lambda and beta with the penalization term lambda times g of x plus beta times h of x. So in this case, if g of x is strictly positive, then we see that we maximize over lambda strictly positive, and this value will be plus infinity. And if h of x is not 0, we penalize, we maximize over any constant beta, and we can make this quantity to be plus infinity again. So when we minimize over x, we will choose, automatically we will choose some x such that the constraint will be satisfied. Okay, so this is a current formulation of the initial optimization problem and the constraint. Now, formally, of course, we need to justify mathematically, but formally, let's exchange the minimization operator and the maximization operator. Okay, and we obtain the maximization, maximize over lambda, and beta, and minimize over x again. And again, look at, imagine that we have optimal lambda, optimal beta, and in this case, we look at the minimization problem, we obtain the Euler's first order condition again. Okay, so now we move to the last slide, slide 7, and we obtain our new first order condition for the optimization problem and the constraint. The new first order condition becomes for some constant lambda positive and some other constant beta such that the gradient of new function is 0. So this becomes the gradient of f plus lambda, gradient of g plus beta, gradient of h is 0. So remember, x star is the optimizer, so x star will still satisfy the constraint g of x star is less or equal to 0, and h of x star is equal to 0. And then also together with the other condition lambda star times g of x star is 0, we can compute the minimizer x star in many concrete cases. Okay. In some other situation, even we cannot compute explicitly the solution x star, the solution of the minimization problem x star, we can still design a numerical algorithm to compute this minimizer x star. So in the next video, our colleague Ms. Shen Yi will give a presentation on the application of the optimization method for optimization problem in finance. Okay, so thank you.